In this next section, I want to begin talking about something that's called the dot product of two vectors, also known as the scalar product or the inner product. The way that we're going to actually calculate this is easy. If I'm in two-dimensional space, the dot product of u and v, which I'm going to write this way, is u1 times v1 plus u2 times v2. If I'm working in three-dimensional space, I'll have one extra term. It'll be plus u3 v3. So calculating this thing, this inner product, is easy if you just want to get the number that it represents. What this is supposed to mean to us, though, is a different story. For example, if we're in two-dimensional space and u is 2 times I plus 3 times j, or using the bracket notation, bracket 2 comma 3 close bracket, and v is 5i plus 6j, then u dot v is 2 times 5 plus 3 times 6, which works out to be 28. This number 28 is supposed to be a scalar. This is a number, but it's also a number that doesn't depend on any kind of coordinate system or anything. We'll talk more about that later. In three-dimensional space, suppose that u was 2, negative 1, 4, and v was 2, 5, 1. U dot v would be 2 times 2 plus negative 1 times 5 plus 4 times 1, which, assuming I've done my arithmetic correctly, is 3. Allegedly, the dot product is a function that depends only on the arrows. You give me two arrows in the plane, and this dot product is supposed to depend only on the arrows. It's natural to wonder if this dot product has any interesting algebraic properties. In the real numbers, a times b and b times a are always the same. It's not hard at all to see that the same is true of the dot product. U dot v is u1 v1 plus u2 v2. V dot u is v1 u1 plus v2 u2. Looking at the two-dimensional case, that is. u1, v1, u2, and v2, though, are just numbers. So this number, u1, v1, is the same as that number, v1, u1, and u2, v2 is the same as v2, u2. So u dot v is the same thing as v dot u, just as you would hope that it would be. There's a commutative law for multiplication. If I call multiplication this vector dot product thing. In ordinary algebra, we have a distributive law. A natural question is there something like this for the vector dot product? So u, v, and w are going to be vectors. A and b are going to be numbers. I'm going to form the vector au plus bv and then dot product that with w. And I want to think about whether or not that's the same as doing the dot product of u and w and then multiplying that number by a, doing the dot product of v and w and taking that number times b and adding them together or not. If you figure out the component of au plus bv, it's easy enough to work out. W has components w1 and w2 in two dimensions. The way we do dot products is I take this number and multiply it by w1, that number, and multiply multiply it by W2, add those together, and I get a rather complicated, messy looking expression. On the other hand, if you look at U dot W, this is U1W1 plus U2W2, I'm going to multiply this number by A, and likewise, I'll have V1W1 plus V2W2 multiplied by the number B. Doing the ordinary distributive law, I can write the result in this form. A U1W1 is that term. B V1W1 is that term. A U2W2 is that term. And B V2W2 is that term. These two things are the same. There is a distributive law for the dot product. Also, if the first thing had been a single vector and the second thing had been some sort of combination like this, the same result will follow. In ordinary algebra, if you multiply a number by itself, say a times a to get a squared, the result is never negative. It could be 0, but that only happens when the number a itself is 0. If you look at u dot u, that would be u1 squared plus u2 squared. Those are actual numbers you're adding together, neither one of which is negative. So u dot u can't be negative, and the only way that it can equal 0 is if u is the 0 vector. Also, if you remember, the way we do the magnitude of a vector, we square the components, add them up, and do the square root. The only difference from that to u dot u is that we didn't do the square root. Another interpretation is u dot u is the length of u squared. So this dot product is going to have something to do with lengths, but there's more to it than that. To figure out what this means to us exactly requires a little bit of thinking. Before I do that, I want to make a comment. This dot product is supposed to take two vectors and return a scalar. Now, two vectors, I can always rig the starting point for the two vectors to be in the same place. We can do this with the Euclidean parallel postulate. So I'll pretend that I've done that already, and not only that, if I've got the initial points at the same place, which I might as well take to be the origin, I'll have one point, the end point of u, and the end point of v. 3 points can be put in a plane. So I'm going to draw my vectors here as though they lie in a common plane, which I might as well call the xy plane. This doesn't hurt anything because I've got exactly two vectors. In 3 dimensions, if I had more vectors than that, it wouldn't be okay to say they all lie in the same plane. If you'll go back and look at the polar form for the vectors that we talked about, vector u can be thought of as the length of u times the cosine sine vector that goes with the u vector. I'll call the angle that u makes with the positive x-axis alpha. So u is actually, in component form, length of u cosine alpha, length of u sine alpha. If I call the angle between v and the positive x-axis beta, I can say that vector v is length of v cosine beta, length of v sine beta. And again, for emphasis, these are vectors, they are arrows. Having expressed the vectors u and v in that format, u dot v is easy to calculate. I take the first component of u times the first component of v, second component of u times second component of v. Both terms have a factor of the length of u and a factor of the length of v, so I will factor those out. What's left is cosine alpha cosine beta plus sine alpha sine beta. There's an old trig identity from trigonometry that says the quantity inside this bracket is the cosine of beta minus alpha, but beta is the angle that v made with respect to the positive x-axis. Alpha was the angle u made with the positive x-axis. Beta minus alpha is the angle between the two vectors u and v, which I'm going to start calling theta. Hopefully this won't cause any confusion with previous uses of the letter theta. So what's u dot v? U dot v is the length of u times the length of v times the cosine of the angle between them. And this convinces me that this dot product thing really is a scalar in the technical sense of the word, because if I have a picture of the situation in front of me, not a picture of any kind of coordinate system or anything, just a picture of the two arrows, and I know the angle between them, I can calculate this dot product without knowing any coordinate system. For example, if I had two vectors u and v, and I measure, say with a ruler, that the length of u is 10 units, the length of v is 8 units, and then I haul a protractor out and I measure the angle between them to be 74 degrees, u dot v is length of u times length of v times cosine theta, 10 times 8 times cosine 74 degrees. This works out to be about 22.0599. I didn't need any coordinates to do this. I just needed to know what the arrows looked like and how one of them is angled compared to the other one. No need for an x-axis or anything like that. In physics, thinking using vectors is frequently very convenient for this sort of reasoning. In this same generic setup, there is a bit of wiggle room though. I've drawn two pairs of vectors, u and v, the same u and the same v in both of them. If I want to speak of the angle between the two vectors, I could be talking about this angle, or if I were insane, I could do that angle. We're always going to make the first choice. We're always going to pick the angle between two vectors to be the one that is positive and no bigger than 180 degrees, also known as pi radians. The reason that we do this is we have a formula that says u dot v is length of u, length of v cosine theta. If you rearrange that formula, it says cosine theta is u dot v divided by the product of the lengths of the two vectors. The inverse cosine can supply me with angles that are between 0 and 180 degrees. So if we adopt the agreement, we're always going to pick the smaller positive angle, then it's legitimate to write this, and we'll never get into any trouble with it. This is interesting. This is relating the vectors, the dot products, the lengths. If I know those things, I can tell you what the angle between the vectors are without drawing a picture, without needing a coordinate system. Let u be the vector 1 times I plus 2 times j plus 3 times k. V be the vector 1 times I plus 0 times j plus negative 1 times k. I'd like to know the angle between those two vectors. If I try to solve this problem by manually drawing little triangles and stuff, it doesn't go too well for me. But luckily, we have ways of doing this sort of thing now. Firstly, the dot product of u and v is 1 times 1 plus 2 times 0 plus 3 times negative 1, which works out to be negative 2. Secondly, the length of u is the square root of the sum of u's components, the square root of 1 squared plus 2 squared plus 3 squared, which works out to be square root of 14. The length of v, you take 1, you take 0, you take negative 1, you square all of those numbers, add them up. Length of v is square root of 2 units. It's worth mentioning I see this mistake in this course a lot. People write 1 squared plus 0 squared plus negative 1 squared, and they'll forget to put the parentheses around the negative 1. They end up with 1 plus 0 plus negative 1, which would be 0, which is obviously wrong. The only vector that has length 0 is the 0 vector, and v certainly isn't the 0 vector. So, not to insult your intelligence, don't make that mistake. Cosine theta is the dot product of u and v upstairs, that's the negative 2, divided by the product of the lengths, square root of 14 times square root of 2 on the bottom. Being lazy, I just wrote the bottom as square root of 28. Because of what we have figured out, theta is the inverse cosine of negative 2 over radical radical 28, which works out to be about 112.208 degrees. So calculating angles between vectors, that's easy now. I want to make this particular video rather short because I'm still having throat problems here. So I'm going to split this up into two pieces. The piece we've already done and what we'll do tomorrow will have to do with vector projections work, and there's a classical problem that every physics book in the world gives you. In elementary physics books, they give you this problem and it's so artificially simple that you think life must be easy. The problem would be you've got an inclined plane. They tell you this angle. They put some object on the plane, and they want to know how much force needs to be exerted along the direction of the plane, which really doesn't even make any sense, to keep it from rolling down the plane. This makes people want to do what they hilariously call the physics way of doing it, which I'm pretty sure makes every physicist on Earth cringe, because this is an overly simplified version of the problem that they give you to get started on. This is where people want to start drawing little triangles and stuff, and I want to avoid that. So instead, what we're going to do is to imagine that we've got our plane, the plane that the object's going to roll down, but I'm not going to do the simple orientation for you. I'm just going to tell you that the plane is at right angles to some vector. This establishes the orientation of the plane, but it doesn't go that far. Put a marble on the plane, hold it still and let go of it. What direction does it roll in? How much force would you have to apply to keep it from rolling down the plane, and in which direction? The facile answer to which direction does it go in is obviously downwards, but there's lots of downwards directions. Which one do you pick out when the problem hasn't been artificially simplified for you? After we figure out vector projections, this will be easy. We are not going to draw the triangle. Not interested. In the meantime, I hope everybody is doing well. I'm very slowly improving. We will be out the rest of this week, definitely, and a chunk of next week. We may do the whole of next week also, depending on how things go. But in any case, I hope everyone's doing well, and I hope you're staying safe. I'll talk to you again soon.